Well, hello again, everyone. Welcome to our discussion of section 2.1. So in this section, we will be talking about these main topics: evaluating functions, evaluating piecewise functions, evaluating the difference quotient, this being a pre-calculus class. The difference quotient, we're setting the foundation for using the difference quotient in the calculus class. So here we introduce the concept, but in the calculus 1 class, you'll see what use the difference quotient really has. And finally, 4, we've talked about the domain of a function, and we'll do more examples of that in this section. Okay, before we start this section, I want to remind everyone to please skim through the textbook section for 2.1, section 2.1, before you watch this video or before you attend the lecture, and then attend each class and take notes and review your lecture notes. And even if you watch the video, take notes of things that questions you might have. And then review your lecture notes and solve all the examples that I'll be working on in this video on your own, once again, a second time, without looking at my solutions. And then, of course, complete all homework assignments by the due date, and throughout the semester, review this material to keep this fresh in your mind in preparation for the final exam. Okay, so evaluating the function. Functions are basically, the basic function is comprised of an independent variable, which we can choose, and then the output variable, which will depend on the quantity we choose for the independent variable. The independent variable is usually known as the variable x, and the dependent or output variable is known as the variable y, or f of x. So here in this table, we are given some quantities, and we need to substitute these in this function and find the y value for them, or f of x. So I hope you pause the video, you calculate these values, and then unpause the video and look at my values here. Okay, so I'm assuming that you have done that and you are ready to join me here. All right, so the function is 6 times x minus 5 squared, right? That's f of x. So the function at x equals -1 would be function at -1 is equal to 6 times -1 minus 5 squared. So -1 minus 5, that is equal to -6, right? And -6 squared is positive 36. So 6 times 36, what do we end up with? 216, right? So that number goes here. Then the function at 0. So then we say 6, 0 minus 5 squared. I'm just plugging in 0 for x there. And then, so the function at 0 is equal to 6 times minus 5 squared, which is equal to 6 times 25, or equal to 150, right? Let's see. 6 times 2, 25. We have 150. And that 150 ends up there. So let's plug in 1 for x in this function. So the function at 1 is equal to 6 times 1 minus 5 squared. 1 minus 5 is minus 4, right? Minus 4 squared. Minus 4 squared is positive 16. 6 times 16 is 96, right? So 96 ends up here. We have two more numbers to evaluate in this function. So let's do that. The function at 2 would be 6 times 2 minus 5 squared minus 3 squared. This would be 6 times 9, right? Minus 3 squared is positive 9. 6 times 9 would be 54. So we'll write that here. And then one more, evaluating the function at 3. So that would be 6 times 3 minus 5 squared. Just plugging in this formula for x with 3, right? And so what do we have? We have 6 times 3 minus 5 is minus 2 squared. Minus 2 squared is 4, positive 4, right? And that is equal to 24. Like that. Okay. All right. So let's do the same thing here for this function, which is an absolute value function. That one. All right, so we're going to plug in for x with negative 3. For x, yes. So this is called g of x. And this should have been g of x, not f of x. Okay, so g of x, or g at negative 3, is equal to 5 times negative 3. I'm just plugging in here with negative 3 plus 3, right? So that would be absolute value of negative 15, absolute value of negative 12, absolute value of 12. Okay, like that. So this 12 goes in here. Let's plug in for x with negative 2 here in the g function. So we have absolute value of 5 times negative 2 plus 3. 5 times minus 2 is minus 10 plus 3. Right? That would be absolute value of negative 7 when you add those two. And we end up with positive 7. And that 7 goes in here. So, in function g, we substitute for x with 0. 5 times 0 plus 3. So that'll be 0 plus 3. Or absolute value of 3, which is 3. And that 3 ends up here. And then we evaluate the function at x equals 1. So we have that absolute value of 5 times 1 plus 3 equals 5 plus 3 equals absolute value of 8, which is 8, and that 8 goes in here. Last one, positive 3, right? Let's plug it in. So the function g at positive 3 would be equal to absolute value of 5 times 3 plus 3 equals absolute value of 15 plus 3, equals absolute value of 18, which is equal to 18. And that will go in here. Okay? All right. So here, making a transition to this kind of question, notice here the argument x not only accepts numbers like what we did in these two examples we just did, not only it accepts numbers, but also other variables. That's also possible. So x can be anything, numbers or other variables, a, negative a plus b. It can be anything. So let's see how this is done. I hope you are pausing the video at this time. Evaluate this function at these quantities, at these values, and then unpause the video and take a look at what I have done. That guarantees that you're learning the material. I hope you're following this advice. I'm just hoping. Okay, so this simply means substitute wherever you see x with letter a or variable a. So we have 4 times a plus 3, and we're done. That's the final answer. This one means wherever you see x, substitute it or replace it with minus a. So 4 times negative a plus 3, that is equal to minus 4a plus 3. This one means wherever you see x, replace it with a plus b, 2 terms. So let's do that. So 4 times, 4 is being multiplied by all of x, right? So it has to multiply by all of this. 4 times a plus b plus 3. Let's distribute. So 4a plus 4b plus 3. Okay. I hope this solution matches what you had written down in your solution. Here, we're doing the same thing, but this time we have a quadratic equation for which, for x value, we have to replace with x plus 1. Okay, so I hope you have your own solution already, in which case that's wonderful. So wherever I see x, I'm going to replace with x plus 1. So 3 times x plus 1. Notice this power applies to all of x. So it has to apply to all of x plus 1, what I replaced x with. Okay, plus 2 times x. So 2 times both terms that are replacing x. Minus 6. Okay, so now I don't want to leave the answer like that. I need to simplify this, which means I need to expand this one, this binomial squared, and I need to distribute this 2 into this and then combine the like terms. So you can either FOIL this one, or if you remember the special product formula, which I have asked you to remember, it makes your life easy now. Quickly you can write this out. So 3 times x squared plus 2x plus 1, and you're done by expanding that. But if you don't remember that, then you can use the FOIL method. But remember, sooner or later, you're going to have to remember those special product formulas. So please spend a little bit of time and remember those formulas. So let's distribute this 2. We have 2x plus 2 minus 6 equals, let's distribute the 3, 3x squared plus 6x plus 3, right? I'm distributing the 3 into this parentheses, plus 2x plus 2 minus 6. So let's combine the like terms. 3x squared, there is no other x squared term here. So 3x squared. 6x plus 2x is 8x. Let's write that down. 3 plus 5 plus 2 is 5 minus 6 is minus 1. So this whole thing is a new function, f of x plus 1. Okay. So now, next, we're going to evaluate this function as at negative x. So wherever you see x, I'm going to replace it with negative x. And let me, because it's going to be, is it still on the screen? Let me see. Yeah, you can still see it. Right? Like that. Okay. So replacing x with negative x, we have 3 times minus x. Notice here the power 2 is applying to the all of x. So once I replace x with minus x, then power 2 applies to all of negative x. Plus 2 times x plus 2 times negative x, right? Minus 6. I hope this is making sense to everybody. So now, let's simplify. Minus x squared is positive x squared. So again, 3x squared. 2 times minus x is minus 2x minus 6 that comes after. So this is f of the function at negative x. Okay. Piecewise function. These are very interesting functions. Not only themselves, how they're set up, which is conditional. So the function is equal to x squared if x values are negative. The function is equal to a linear function if x values are 0 or positive. So piecewise functions are conditional functions. They are multiple functions within one function. They are piecewise. Okay? For this piece of the xy plane, you have this function. For the next phase or next segment in the xy plane, you have another function. It's multiple functions within one function. And their graphs behave accordingly. And I think in this course we will get to those later at some point. So we have to be aware of where each x value falls, and we'll have to use the relevant function. So here we have negative 2. Negative 2 is an x value that is definitely less than 0, right? So if that's the case, then this is our function, x squared. So let's substitute for x with negative 2 squared. We'll have positive 4. This is negative 1. Negative 1 is certainly less than 0 or a negative number. So we're still using this function, x squared. So minus 1 squared, we have positive 1. Because this 2 applies to the negative as well as to the 1. This 2 applies to the negative as well as the 2. Okay, so positive answers there. Now 0, x value 0, where is it? It's in here, right? It's in this condition that x is allowed to be either 0 or greater than 0, something positive. So our function is this, x plus 3 equals, so replace x with 0 plus 3 or 3. 1 is definitely an x value that is greater than or equal to 0, right? So our function is that, x plus 3. Let's replace x with 1 plus 3. We have 4. Okay? So 20, x value 20 is definitely greater than or equal to 0. So this is our function, x plus 3. Replace x with 20 plus 3. We end up with 23. Okay. Here's another piecewise function. One correction I need to make here, and I should remember to make the correction in the worksheet that I have on my computer, is that the condition that x can be less than or equal to -1, this -1 should be either part of this condition or part of this condition. And 1 should be, 1 is okay actually. It's the -1 that I need to correct, this condition. So if x is less than or equal to -1 as part of this condition, then I have to remove -1 from this condition. So this should be strict inequality, like that. Okay? It shouldn't have the equality under it, because -1, x being equal to -1 is already part of this piece of the function. It cannot be part of this piece too. It should be either part of that piece or this piece, or this piece. Okay, so that I needed to make that correction. Okay, so now having made that correction, let's answer these. And I hope that you guys go through this with your own scratch paper, answer all this, and then come back to the video again. Okay, so -4, these are x values, right? That's x equals -4. So x equals -4 is definitely less than -1, which means our function is this, x squared plus 2x. So let's plug into that function with x equals -4. -4 squared plus 2 times -4. -4 squared, it's going to be positive 16. Positive 2 times -4, minus 8. 16 minus 8, positive 8. Okay, so -3/2 is definitely, again, less than an x value that is less than or equal to -1, right? So that's our x value. So once again, our function is x squared plus 2x equals, let's replace x with -3/2. So -3/2 squared plus 2 times -3/2. Okay, so -3/2 squared, it's going to be positive 9 over 4. 2 times -3/2. This 2 and this 2 cancel each other out. We end up with -3. Okay, so we have to take the common denominator, right? We know that -3 has denominator 1. What is the common denominator? It's 4, right? So because it's 4, this fraction is happy. Its denominator is already 4. So we don't have to multiply this fraction by anything. But this one has a denominator equal to 1. So we need to get this denominator equal to 4. So we have to multiply it by 4. But we can't do this to the denominator, not do the same thing to the numerator. So 4 times the numerator, 4 times the denominator. Okay, so what do we have? We have 9, then the 4 is there, minus 3 times 4 is 12. So the final result is 9 minus 12 is -3 divided by 4. By the way, this answer is the same answer that if you write it as -3 over 4 or 3 over -4. All of these answers are the same thing. Okay, this is okay, this is okay, that is okay. Okay, so this one is asking us to evaluate the function, the piecewise function f at x equals -1. So this is our x value. Well, x equals -1 is still that function. So we're still using this function, x squared plus 2x, plug in for x with -1. -1 squared is 1, plus 2 times -1 is -2, equals -1 minus 2 is -1. Okay? So, this one says evaluate the function, piecewise function for x equals 0, right? X equals 0 is in this condition. If x is between -1 and 1, and 0 is between -1 and 1, then f of x equals x. So here, this is equal to x. Replace x with 0, we have 0. Okay? X equals 25. So 25 is definitely greater than 1, right? So if x is greater than 25, the value of the function is always equal to -1. So what is the value of function for x equals 100? -1. What is the value of this function for x equals 10,000? -1. What is the value of this function for x equals 10 billion? -1. For any x value greater than 1, the value of the function is always -1. So it's a vertical line. Okay, sorry, it's a horizontal line. So for x values greater than 1, so let me draw a basic sketch graph of that so you can see what I mean. So just for this piece, I'm going to draw the graph just for that piece. So if we have like that, so what that is saying, for any x value greater than 1, suppose we have, this is 1, and so I'm going to put a hollow circle because x cannot be equal to 1 here, then the value of the function is equal to -1. So let's say that's -1. That means starting at x equals 1, which is somewhere here, and I'm going to put a hollow circle there. Let me put the -1 on this side. So at that point, the value of the function is always -1. The equation of this line is y equals -1. Okay, that's how that piece, just the bottom piece, would plot. Okay, I wanted to show you how it looks. So x is increasing to infinity, but the value of the function remains at -1. Okay, so that's why at x equals 25, the value of the function is going to be equal to -1. Okay, it's going to be on that horizontal line that I just drew. Okay, so this next topic is the difference quotient. The difference quotient, as I said earlier, becomes very, very important beginning in Calculus 1. It leads to the definition of a changing slope, which is the derivative, but that's for Calculus 1. But now we're just introducing it, so it doesn't look all new to you when you see it in the Calculus 1, and also that you're familiar with the algebra of the difference quotient. So this is called, you'll see this name again and again, so I want to make sure that you're familiar with the name of the formula as well as how it looks. So this is called the difference quotient. Okay, so all it is, it says starting with a preliminary function, find the value of a new quantity that is based on that function evaluated at some other quantity. So this is saying you find the difference quotient where h is never 0. So h, we really don't, in this class, h has a meaning in calculus, but in this class, we just accept it as another variable that cannot be 0. That's all. So now, let's calculate this quantity. How are we going to be able to calculate this quantity? Well, first, we need to calculate the function at a. Then we need to evaluate this function at f of a plus h. Once we have those two quantities, then we should take the difference and divide by h and simplifying the process. So let's do that. I'm gonna start with the easier one. Let's find f of a. So f of a is equal to 7 times a plus 2. Again, I think at this point, even though the difference quotient might be some new quantity to you, but the path to evaluating it, to calculating it, you already know all the tools necessary for that. So I hope you pause the video, calculate, find your own answer, and then compare it with mine. And if you've already read the section briefly, say for half an hour to 45 minutes, you already have a pretty good idea of what this example is asking you to do. Okay, so I just replaced x with a and I got this result. Now I have f of a, but I don't have f of a plus h. So let's find f of a plus h. So in this function, wherever you see x, just replace it with a plus h. So 7 times a plus h plus 2, right? Then let's simplify or distribute. So we have 7a plus 7h plus 2. So now we have f of a plus h is that, right? F of a plus h is that. F of a is that. So now we can calculate this quantity. We can subtract f of a from f of a plus h in the numerator and divide by h. So let's do that. So given that, we're going to plug in with what we have. F of a plus h is all of that, right? So 7a plus 7h plus 2 minus f of a. F of a is all of that. 7a plus 2. So it's critical that for you to remember to put the parentheses around this, because that negative symbol or sign is not a neutral sign. It's going to distribute itself into all of f of a. And all of f of a is not just 7a, it's 7a plus 2. So that minus will distribute itself or multiply itself by everything that is in f of a. Okay, so all of that divided by h. Okay, so let's simplify. I'm going to write this first part as it is, 7a plus 7h plus 2. Now we have to distribute this negative into this. So minus 7a minus 2 divided by h. Okay, so let's simplify. What do we have? Negative 2 plus 2 add up to 0. Negative 7a and 7a add up to 0. We end up with 7h divided by h. And h cancels out, and instead you get 7. Okay? So let's do another example. Please pause the video, answer this question, then come back to the video and compare your solution with mine. Okay, I'm counting on you having done that, and now you're ready to see my solution. So here, another difference quotient, right? Quantity calculation. So first we need to find f of a, then we need to find f of a plus h, then we need to subtract, divide by h, and then simplify, like I did. So let's do that. F of a is equal to a squared plus 9, right? All I did was replace x with a. So f of a plus h would be the same thing, but instead of x, we're going to have a plus h squared plus 9. Notice how I'm replacing all of x with a plus h. Okay, and now I have to expand this binomial squared. We have to expand it. If you memorize the special product formula, you can do it very quickly, which is a squared plus 2ah plus h squared, and then plus 9. So we now have f of a, and we have f of a plus h. So now we can calculate this quantity. This quantity says take f of a plus h, which is all of that, right? And then subtract from it minus all of a, all of function at a. All of function at a is this, a squared plus 9. That's why it's so important for you to put this parentheses, because this negative must distribute itself into both terms. I've seen so many times people write minus 8a squared plus 9. So they assume this minus belongs to just a squared. No, it must distribute itself to all of f of a. F of a minus f of a. F of a is a squared plus 9. All of that divided by h. Okay, so let's distribute this and simplify. We have a squared plus 2ah plus h squared plus 9. That's all of what you see here. Now we have to distribute the negative. Minus a squared minus 9 over h. And let me come up here for the rest of this solution. Okay, so now negative 9 and plus 9 add up to 0. Minus a squared plus a squared add up to 0. We end up with 2ah plus h squared divided by h. Okay, then can we simplify this? Absolutely. Factor out h. So h times 2a plus h divided by h. I hope you see clearly how I factored the numerator, because if you distribute the h back into this parentheses, you're going to get what we started with. And that's the idea behind factoring. It's the opposite of the distributive property. So whenever you factor, you can quickly test your own work by redistributing the variable or the term that is on the outside of the parentheses and see if you get the original expression that you factored back. If you do, your factorization is correct. If you don't, then you have to correct what's missing or the error in the factorization. But if you multiply or distribute h into this, you get 2ah. If you distribute h into h, you get h squared. So everything is okay. Now, the h and the h cancel out because the h in the numerator is being multiplied and then divided by another h. So the final result then is 2a plus h. Okay. Here's another difference quotient calculation. Let's go through that. Okay, so we have, again, we have to calculate f of a. We have to calculate f of a plus h, and then subtract, divide by h, and simplify to find the final answer. And excuse me while I drink a little bit of water here. Okay, I hope you have already solved this. If you haven't, please pause the video, run through this solution on your own, and then come back and compare it with the work that I will be doing. Okay, so let's calculate f of a and f of h, a plus h first. So f of a, wherever you see x, I'll have to replace it with a. So a, 8 minus 7 times a plus 2 times a squared, right? So what do we end up with? We end up with 8 minus 7a plus 2a squared. That's a. So now let's find f of a plus h. f of a plus h means wherever you see x, replace it with a plus h. So 8 minus 7 times a plus h plus 2 times a plus h. Notice the power 2 applied itself to all of x. So the power 2 here must apply itself to all of a plus h, which is what we replaced x with. Okay, so now there's quite a lot of simplification work we need to do before we can evaluate the difference quotient. Let's do that. So this equals 8 minus 7 times a minus 7a minus 7 times h is minus 7 times h plus twice expand this using either the special product formula if you remember it, or FOIL it in case you don't remember that. So a squared plus 2ah plus h squared. So let's distribute the 2 into that and see what we can or cannot combine in this equation. So 8 minus 7a minus 7h plus 2a squared plus 2 times 2ah is 4ah, 2 times h squared is 2h squared. So, is there anything we can, let's see, is there anything we can simplify? Do we have another constant beside 8? No. Do we have another a term besides minus 7a? No. Do we have any h terms besides minus 7h? No. That's ah, not h. And that's h squared, not h. Do we have any other term with a squared in it? No. Do we have any other term with ah in it? No. Do we have any other term with h squared in it? Absolutely not. So there's nothing we can combine here. We have to keep it as it is. Okay. So that piece, all of that is a plus h. Okay. Now we have to apply what we have to the difference quotient. So the difference quotient says take f of a plus h, which is all of that. That's all of that is f of a plus h. So let's use that. 8 minus 7a minus 7h plus 2a squared plus 4ah plus 2h squared. Take all of f of a plus h. Subtract from it f of a. Subtract from it all of f of a. What is f of a? F of a is these three terms. Right? So minus 8 minus 7a plus 2a squared. So this means it's very, very important. Now, the first parentheses, I'm just using it as a visual aid, just to show you that all of this is a plus f of a plus h. All of that is that. Minus is minus, but this parentheses, this pair of parentheses, these two, are very important for you to remember to use, because if you forget it, then you'll distribute this minus only to 8 and not to the other two terms, which will cause a huge error. So the parentheses indicates that this minus in front must multiply itself by all the three terms. Okay, so all of that divided by h. Okay, so the next step for us is distribute this minus into this and combine with what we can with these terms. Okay, so we have, I'm going to rewrite this piece down for now. 8 minus 7a minus 7h plus 2a squared plus 4ah plus 2h squared. Now let's distribute this into all of that. Minus 8 minus times minus 7a, positive 7a, minus times positive 2a2 minus 2a, or 2a squared, sorry, minus 2a squared, all of that over h. So let's see what we can simplify and what we cannot. Do we have another 8 here? Yes, we do. 8 minus 8. They add up to 0. Do we have another 7a there, or any a term? We do. Minus 7a, positive 7a. They add up to 0. Do we have another h term? No, that's the only h term. So we have to write it down. Minus 7h. Do we have another a squared term? We do. They're equal and opposite. So this one and this one add up to 0. Do we have another ah term? No, we don't. So we need to write this down as it is. Do we have another h squared term anywhere? No, that's the only one. So plus 2h squared. We're done combining the like terms over h. Is there anything we can do to simplify this result? Absolutely, right? Look at the numerator. What can be factored from the numerator? Can we factor out 2? Well, not really, because negative 7 would not allow us to do that. Only 4 and 2 have factors of 2, have a factor of 2, but not minus 7. Can we factor out h? Absolutely. All 3 terms have h in them. So let's do that. So this is equal to h times minus 7 plus 4a plus 2h. All of that divided by h. Right? So now, can we do something to simplify? Absolutely. This h and this h cancel out, and we end up with minus 7 plus 4a plus 2h. Yes, that's correct. So I should double check these later before posting my lecture notes on Canvas, just to make sure that there is no error in this. Let's see, 7x, 7a minus 7. I'm just quickly checking to see if everything is all right here. 4a plus 2h. Yes, that should be correct. All right. So once again, we arrive at the doorstep of the domain. Domain is very important because it tells us where the function is valid and can be used and where it's not relevant at all. So that's why it keeps coming back up again and again and again throughout this course, and we will see it again down the road. So domain is basically all values of the independent variable, that one, which usually happens or taken along the x-axis, minus any restrictions on x. And we've already talked about, when we did some examples of finding the domain in the past, we talked about if you have a square root, the inside of the square root cannot be negative. That's one restriction on the domain. If you have a fraction with an x term in the denominator, we have to make sure that x takes only those values that lead to denominator values other than 0. The denominator can never be 0. So all of those put restrictions on the independent variable value and restrictions on the domain of a function. So that's what, I mean, part of these worksheets is for you to also read. So not all of these worksheets have to do with solving examples, but I've put things for you to read and remember as we solve domain problems. So this is exactly saying what I was saying a few seconds ago, that the denominator of a fraction cannot be 0, and inside of a square root function can never be negative. Okay. All right. So one note that I've made here, it's because polynomials come up a lot in algebra. All the quadratic equations that we've been solving so far, these are polynomials. And so one important thing to remember about polynomials is that the domain of a polynomial is always negative infinity to infinity. So as long as you have a polynomial, you already know that the domain of a polynomial is negative infinity to infinity. That's another way of saying there are no restrictions on the domain of a polynomial. It accepts all values of the independent variable for the independent variable. So all real values are possible in a polynomial. Okay, and that's the note about that, which I'm mentioning here. So having just discussed these points briefly, which we've already discussed, at least the first two we've talked about this before, but this one may be new to you, that the domain of a polynomial, and that's what you see here is the general equation of a polynomial, that one, all the way to A, all the way to here. That's the general equation of a polynomial. Okay, so first example says find the domain of the function and write it using the interval notation. And I hope that you pause the video at this point and solve this on your own and then come back to the video again. I'm counting on you to be doing that. Okay, so the domain of this function must guarantee that the denominator is never 0. So let's solve for any x value that could make the denominator equal to 0. So 3x minus 15 equals 0, and 3x equals 15, and x is equal to 15 over 3, which means x equals 5. So the domain must exclude this. And the function undefined. Okay? So you don't have to draw this graph, but I'm drawing it just to make sure that everybody understands what we're doing. So this is the real number line with the 0 in the middle, and we've just decided that x equals to 5, which is somewhere here, cannot be part of the domain. So what can be part of the domain? This piece and this piece should be part of the domain. Not 5, but anything on this side, the left side, and anything on the right is acceptable. Okay, so that's how we write it. Negative infinity all the way to 5, parenthesis or bracket. If you said parenthesis, wonderful, because 5 should be excluded, and parenthesis means 5 is not included as part of the domain. Union, parenthesis 5, comma, infinity, and this is the domain. And this is the interval notation. They're saying write your domain using the interval notation, and that's what they're talking about. Okay. The second, so I hope you pause the video, or I encourage you to pause the video, write down your own domain, find the domain, and then come back to the video to see the solution. Okay, so here, do we have to worry about the numerator? No. There is no x value in the numerator that should be restricted. All values of x in the numerator are okay. Okay, but how about the denominator? Well, in the denominator, it's a different story. We have to solve for this expression when it's 0 to make sure that we exclude those values that make this denominator equal to 0, right? Because for that, the function would be undefined. So x squared minus 4 equals 0. Then x squared equals 4. Then x equals 2. Is that answer correct? It has an error. Is that correct? Or what's wrong with it? What's wrong with my solution right now? Think about it. Well, it should be plus or minus 2 when you take the square root of both sides. Right? X squared equals 4. But we take the square root of both sides. So that would be, the other side would be plus or minus when we have x squared on this side. Okay, so those two values should be excluded from the domain. Okay, because plus or minus 2 will make this denominator 0 and the function undefined. Okay, once again, you don't have to draw this graph, but I'd like to draw it so people have something visual about the final answer, to associate it with the final answer. So we have the real number line. Positive 2 would be, let's say here, we can't have positive 2 as part of the domain, and negative 2 would be somewhere here, and we cannot have negative 2 as part of the domain, so I'm putting a hollow circle there. So what is the domain then? The domain is anything on this side, anything in between here, and anything on that side. So let's write the domain for each piece. So from here to here, we have negative infinity to negative 2, parenthesis or bracket? Parenthesis, because negative 2 is not acceptable. Union, another parenthesis, negative 2 comma 2, that's that piece, negative 2 comma 2, parenthesis or bracket? Parenthesis again, because 2 is not acceptable. Union from 2 to positive infinity, like that. Okay, does this make sense? How we find the domain? I hope it does. Okay, so here, again, we need to find the domain of the function and write it using the interval notation. But here, we don't have a fraction. Instead, we have a square root. Whenever you have a square root, you cannot have a negative number in there, at least not now, because we're not talking about complex numbers. The complex numbers come along later in the semester, and we have a short section we talk about it. But for now, we're just considering all the real numbers as part of the domain. Okay? So we need to guarantee that this inside is never negative. How can we guarantee that? Well, we start the solution with a condition. And the condition is that x minus 5, or what's inside, or the radicand, should be either equal to 0 or greater than 0. So that means, can it be 0? Yes. Square root of 0 is 0. I mean, here. There's nothing wrong with that. We can calculate it, and we can prove it. So square root of 0, right? Let me hit enter. It's equal to 0. So this inside can be 0, and it can be anything positive, but it cannot be negative, and that's the condition for that. X minus 5 must be equal to or greater than 0. Okay, so using this condition, let's solve for x. We have x must be greater than or equal to, move the negative 5 to the other side, it becomes positive. So x greater than or equal to positive 5, let's write that using the interval notation, which is what they're asking us. So the domain of this function is parenthesis or bracket. So if I put 5 comma infinity, what should I put here? Parenthesis or bracket? If you said bracket, wonderful. Because indeed it's bracket, because you have this equality. So x can be equal to 5. And the bracket means that. Means 5 is part of the solution, part of the domain. Then infinity, parenthesis or bracket. The infinity side, whether it's negative infinity or positive infinity, always gets the parentheses because we can never reach infinity, so it's always excluded. We can approach it as much as we want, but we can never actually get there. So parenthesis means that infinity itself, even though we can approach it, it'll never be part of the solution because we can never reach infinity. Okay, so that is the domain of that. Now the next example, and sorry, let me make that darker so you can see there was a square root here, right there. So we have a square root of 4 plus x divided by 1 minus x. These examples are always interesting because, see, one of the previous examples, see that one? Here, we didn't have to worry about the numerator because there was no special circumstances there. We didn't have another fraction there. We didn't have a square root there. Everything was acceptable in the numerator. It was the denominator that was an issue. Okay? Here, both the numerator and the denominator are special cases. I mean, you have to consider where the domain is restricted for the numerator and for the denominator. So if I write, so if we look for restrictions in the numerator, so let me write that down. In the numerator, four plus x can never be negative, right? Just like that, because we have a square root. We can never have negative in there. So 4 plus x must always be greater than or equal to 0. And that means, let's solve for that, x must always be greater than or equal to negative 4 in the numerator. That's the restriction we must observe in the numerator. So in the denominator, we have the restriction that this denominator can never be equal to 0. So 1 minus x, let's solve for that value and then exclude it from the domain. So then x equals 1. So the domain can never be equal to 1. Right? The x value can never be equal to 1. But if you look at what the numerator is saying, the numerator is saying, oh, 1 would be fine. I mean, let's graph these. Right? Let's graph both the numerator and the denominator values. So x equals negative 4. Like that. And x equals 1. Right? Right there. So this result from the numerator says that, hey, all of these values are fair game, are okay to include in the domain. Right? That's what that is saying. The denominator says no. All variables are okay except 1. So we cannot have that 1. Okay? So where do they overlap? Because this denominator says that is okay, but 1 is not okay. So the final domain for this function, g, is wherever both of those conditions, both of those restrictions overlap. So we need to write the domain so it satisfies the numerator and it satisfies the denominator. Let's do that. So the overlapping piece is from -4 to 1. Should I use parenthesis here or bracket on the -4 side? Can the function be -4? It can. If you substitute -4 here, you get 0 in the numerator, and -4 is certainly okay in the denominator as well. So this side, the left side, will get a bracket. So -4 can be part of the solution. How about 1? Can 1 be part of the solution? No, because 1 will make the denominator 0. So it gets the parenthesis. Union the other piece that is overlapping. After 1, so parenthesis 1, after 1, none of these have any issues with that, right? It's just at 1 that things start to get problematic in the denominator, and it's also anything less than -4 or -5, -6, something like that, that would be problematic. So anything greater than 1 satisfies both this condition and this condition. So we have that. Okay, so this is the domain of that function. So you find the domain for the numerator, the domain for the denominator, and the final domain for the entire function must satisfy both of those restrictions that you came up with in the numerator and the denominator. Okay. This next one, again, please pause the video. Use your own scratch paper to solve this. Find the domain, write the domain using the interval notation, and then come back to the video to compare your result with mine. Okay, so here, once again, the numerator has a square root in it. That means in the numerator, x can never be something negative. So x must be either equal to 0 or greater than 0. Okay, so that's the condition in the numerator. In the denominator, of course, we cannot have that equal to 0, that expression. Well, how do we know where this expression is equal to 0? We can either use the quadratic formula for that, or if we can find a factor, we might be able to factor things here. Okay, let's see. Factoring it would be much easier and quicker than using the quadratic formula. So let me use a scratch paper here to see if I can factor that expression. So to get 9x squared, one option, we can do 3x times 3x, that will give us 9x squared. But I'm looking at the difference between these two numbers. So I'll pick, as my first guess, I'll pick 9x times x, 9x squared. Then how are we going to get two numbers that would multiply to -1, and then such that then the x terms end up being positive 8x. So let me do this. Let me put a positive 1 here and a negative 1 here. I think this factorization is correct, but let's see. 9x times x is 9x squared. -1 times 1 is -1. So where are the x terms are coming from? That should add up to 8x. Let's see. 9x times 1 is 9x. -1 times x is -x. 9x minus x is equal to, these two will give us positive 8x, which is what we have. So this is the correct factorization. This is the correct factorization of the denominator. So let's write that down. So we have 9x squared plus 8x minus 1 equaling 9x minus 1 times x plus 1, right? So This was important because we need to find out what makes the denominator equal to 0. Now that we have the factors of the denominator, we can set each one equal to 0 and solve for the value of x that would make the denominator equal to 0. Let's do that. 9x minus 1 equals to 0. That means 9x equals 1. That means x is equal to 1 over 9. So that's one of the values that would make the denominator equal to 0. Let's find the other one. X plus 1 equals 0. That would mean x equals negative 1. Also another x value that would make the denominator equal to 0. So we need to exclude both of these values from the denominator while we're satisfying this condition in the numerator. So before we write down the final domain, let's draw a graph of what's happening here. Okay, so from the numerator, what this is telling us is all of these values are the solution of the domain. From the denominator, we learn that no, negative 1 is not a solution. X equals 1/9, let's say here, also not a solution, but everything else is. So the denominator is saying just take out those two values and you're okay. Everything else is the solution. But the numerator says no, only these values are the solution. Anything equal to 0 or larger than 0. So we need to find where the domain satisfies all these conditions. Okay, so let's write it down. We have the domain equally. We can certainly not be on this side, right? That means we cannot accept -5, -10. None of these answers because of the restriction in the numerator, which is that. So we can only be on the positive side of the x-axis, or the real number line, the real number line. Okay? So, but on that side, we have to exclude 1 over 9. So we have, if I put 0 here, comma, 1 over 9, let me ask you, should I put a parenthesis here or a bracket? Can we have 0 as part of the solution? Can x be 0 in that function? It can, right? The denominator cannot be 0, the whole denominator, but x itself can be 0, so we can put a bracket next to that. Now all the way, so our domain will be this piece and this piece. But we have to be careful how we write it. So 0, it gets the bracket because it's included in the domain. Picking x to be 0 does not cause any issue here. Take a look at the function. Now, all the way to 1/9. So should I put a parenthesis here or a bracket? If you said parenthesis, you're absolutely right, because 1/9, for x equal to 1 over 9, this denominator is going to be 0, and we can't have that. So parenthesis. Union, then the second piece is, let me put 1 over 9 and positive infinity. Should I put a bracket or parenthesis next to 1 over 9? Parenthesis, right? Because 1 over 9 cannot be part of the solution, and we know that the infinity side always gets the parentheses. So that is our domain for that function. Okay, I hope this all is making sense. If not, please let me know with your questions. So we have come to the conclusion of another section 2.1 here, and thank you for persisting through these videos. And for now, have a nice day, and I'll see you next time.